In this lesson, I'd like to chat with you about star composition. In other words, what are stars made of and how do we know? Well, first of all, let's chat about this very famous man right here, Edwin Hubble.
Born in Missouri in 1889, Edwin Powell Hubble developed an early passion for astronomy after receiving his first telescope when he was just 8 years old. In 1917, whilst working on his doctorate, Hubble received a life-changing job offer from George Ellery Hale, founder of the Mount Wilson Observatory in California. But the opportunity came at a bad time. The United States had just entered World War I, and Hubble enlisted in the military. In 1919, Major Hubble returned from the war and immediately travelled to the Mount Wilson Observatory. Still in uniform, he arrived and announced that he was ready to start observing. In 1923, Hubble made his first important discovery using the most advanced technology of the time, the 2.5-meter Hooker telescope. Measuring the distance to pulsating stars, known as Cepheid variables, he discovered that they reside in galaxies outside our own. At the time, the prevailing view was that the universe consisted only of the Milky Way galaxy. Hubble's discovery that our galaxy is just one of many forever changed the way we view our place in the universe. Following this groundbreaking discovery, Hubble began to sort and classify the galaxies he discovered. He arranged them according to their visual appearance, into spirals, ellipticals, lenticulars, and those with an irregular appearance. This became known as the Hubble sequence, and it is still the most popular system for classifying galaxies. "30 years after Edwin Hubble's death, NASA and the European Space Agency christened their new space telescope after Edwin Hubble. Hubble was the obvious choice when naming a new observatory that would revolutionize the field of astronomy. Edwin Hubble changed our perception of the universe and our place within it, and his spirit of discovery lives on today through the Hubble Space Telescope."
Now, Hubble is a man who did a lot of work on astronomy in the early 20th century or 1900s, and he is famous for saying these three things. He said there are other galaxies outside the Milky Way. What's the Milky Way again? This is the Milky Way. You can see it forms a whole strip of stars that are so close together because we're looking through the spiral galaxy that we actually see them all sort of like as if they're in a line. They're actually extremely far apart, but you can't tell that when you're looking at the galaxy from the side. So he said, we are not alone. There are other galaxies outside of the Milky Way. He also said that almost all of the galaxies are actually moving away from each other.
Hubble's greatest achievement came in 1929, when he determined that the light we receive from galaxies is redder the further away they are from us. From this, he was able to deduce that the further away a galaxy is, the faster it recedes. Named Hubble's law, the observational discovery of this relationship overturned the conventional view of a static universe and demonstrated that the universe itself was expanding.
So here's a picture again of the stars. How would Edwin Hubble, looking at these stars, have come to the conclusion that they were moving away from each other? And then you look at his third proposition, and that is that the farther away the galaxies are, the faster they are moving. Well, first of all, Hubble looked at the light spectrum. Now, the visible part of light is actually a very tiny portion of a very large electromagnetic spectrum that's possible. This is basically just light energy that's coming out of the sun, and most of it you cannot see. So, for example, you can't see radio waves, which are the largest or longest wavelengths for electromagnetic spectrum. And then you get down to infrared just before you hit the visible portion. You can see this is a full continuous spectrum of light, right from the longest red all the way over to the blue end or the violet end of the spectrum, which would be the shortest wavelengths. And then we continue through UV rays, which is what gives you your tan in the summer. And they get shorter and shorter and shorter until we get X-rays and then gamma rays. Grade 10 is going to focus on this entire electromagnetic spectrum, but for our purpose today, we're just going to zoom in on the visible light spectrum itself. All elements have their own distinct spectral pattern, which is basically a banding color pattern that happens when you look through a special device called a spectroscope. Let's take a look at this short video to explain what I'm talking about.
You'll know that light, of course, is made up of many wavelengths, many frequencies, and if we spread out their wavelengths or spread out their spectra, we get this continuous spectrum from long wavelengths to short wavelengths. If we pass that light through a gas, then certain frequencies or certain wavelengths of light are absorbed by the gas, and we'll get the continuous spectrum minus these wavelengths. And so what we have here is an absorption spectrum. And in this case, these are the lines that represent what hydrogen would remove from the spectrum. If we were to allow the gas to heat up, it may emit that light. It'll be only specific due to the chemical nature of this gas. So in this case, we have emission spectrum. And so these are the lines that represent, again, hydrogen. And you'll notice these two are complementary. So the lines that are missing here are the lines that are up here.
This is one of our funnest demonstrations to show atomic spectra. I'm going to show the spectrum of an incandescent bulb, which is continuous. And then I'm going to show the spectra of 4 different elements: mercury, nitrogen, neon, and especially hydrogen. So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. It's called a grating, and this allows you to resolve the spectrum of a source of light in the same way that a prism will resolve a spectrum. So what we're going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with the diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left you'll see a rainbow spectrum that shows what wavelengths are present in this. You'll see, as you look on the right side, violet through all the colors of the spectrum all the way through red. So that's a continuous spectrum. Now what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. So this is a mercury spectrum. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum. So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. This is neon. There's a beautiful orange look to it, And when the diffraction grating is in place, you see a large number of red and orange lines. This is exactly what's used for neon lights. So this is hydrogen. It has a reddish cast to it. And when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line. And it is very important in star images. A lot of nebula in the sky have hydrogen alpha line as one of their prominent spectral lines.
Now let's start looking at how spectroscopy is used in astronomy. So the first thing is chemical composition. And before we look at the chemical composition of, let's say, our sun, let's remind ourselves that we have here three emission spectra for three different elements. So here we have hydrogen, here we have calcium, and here we have mercury. And you will see that the pattern of lines are very different. In fact, they are sort of like the fingerprint for each of these elements, because each of these elements remove very specific frequencies if it's an absorption spectrum, or emit very specific frequencies if it's an emission spectrum. So in other words, if you know the pattern here, if you know the wavelengths that are associated with the emission spectrum, you can determine the element that's causing that. So now let's have a look at the spectrum of our sun, and you'll see we have a whole series of lines, and this of course is an absorption spectrum. Now all of this is due to the light that is passing through the photosphere of the sun. Now that is a gas layer around the sun that is a little cooler than the surface of the sun, which means that gas is going to remove or absorb some particular wavelengths depending on the chemical composition of the photosphere. Now this set of lines are often referred to as the Fraunhofer lines. They don't represent a single particular chemical. There's a whole series of chemicals that are causing this. But if you know the positions, you can determine which chemicals they are. So for example, if we look at G over here, we look at F over here, and C over here, these are all lines that are associated with hydrogen. And that's not surprising because our sun, a star, ultimately is mainly hydrogen. If we look at these sets of lines here, that's indicative of helium. And again, that's not surprising because hydrogen is being fused into helium. That's the process of which the sun works. But there are a whole series of other elements here. I'm not going to go into great details, but for example, K and H over here are indicative of the presence of calcium ions. So if you know what wavelengths are absorbed by various chemicals, you can determine the chemical composition of a star by simply analyzing its absorption spectrum.
Let's take a quick look now at one of the gizmos that are available. Click Show Labels so you can see which stars they are. Let's just choose star number 1. What we have here is the spectra that would be formed if you were looking at star number 1. Now we have two options here. We can look at the neutral spectra, which means that every element that's represented here is going to have an equal number of positive and negative particles, so an equal number of protons and an equal number of electrons. Or we can look at the ionic spectra, and you can see it's ever so slightly different banding pattern, and that's when you have stripped or added electrons. Now in this case here, the hydrogen, the helium, the sodium, magnesium, calcium, and iron, for every single one of these would become positively charged because you would rip off electrons from these guys. Let's start with the neutral spectra though. Okay, what we're going to do is just take the spectra created by this particular element. So this is hydrogen, the labels are below, and I'm just going to bring it over and see if I can match it. And sure enough, you can look and see that the banding pattern lines up. So we can confidently say that in this particular bluish star, we definitely have hydrogen present. Then we can grab helium and do the same thing. And what do you know? The banding patterns line up. So we can say that this star has both hydrogen and helium in it. But when we grab the sodium bars, we see that when we line them up, they do not line up. So sodium is not present. Magnesium is not present. Calcium is not present, and you can guess iron is not present either. Okay, so we can confidently say that in star number 1 we have hydrogen and helium present, but none of these other ones. Don't forget to also check the ionic spectra though. Notice between the neutral and the ionic spectra, just look at hydrogen's bands right now. Notice that it does not change for this particular assignment. Okay, so yep, hydrogen, we confirmed that earlier. We look at helium, nope, not charged. Sodium, nope, not charged. Sodium there. Is there charge? No, because it doesn't quite line up. There's missing bands. Calcium, definitely not, too many bands. And then iron. Okay, so we can confirm that there are none of the ionized versions of these elements here. So just hydrogen and helium in the neutral spectra.
So now here we have a chart that shows you the absorption spectra for various classes of stars. Now the numbers here represent subclasses or subgroupings of each of those classes. So for example, A class, which is of a particular temperature, can be divided anywhere between A0 and A9, and so therefore here we have 2 A-class stars, but the A5 is slightly cooler than, let's say, A0. What you'll notice here is that the absorption lines are not all the same. So if we analyze the absorption lines of a star, we can determine more in detail the temperature of that star, because certain temperatures have certain features in terms of their absorption lines. The first thing I want to show you is that if you want to look at the A-class star, you'll see that our hydrogen lines here and here and here are significantly strong. And so that's one of the hallmarks of an A-class star. They have very strong hydrogen lines, but weaker in other lines. If we look at O and F, there we'll notice that the hydrogen lines are there, but they're somewhat weaker. But how do we differentiate between our O stars and our F stars if they're weaker ones? Well, we now have calcium lines here, which are now stronger. So one of the hallmarks of, let's say, an F-class star is we have weak hydrogen lines, but we have stronger calcium lines. So you'll notice that the calcium lines in the O-class star is significantly weaker. If we then go to G-class stars, you'll see that the hydrogen lines are weaker again, but now you'll also start to get obviously strong calcium lines, but also some other metals appearing as well. And you can see these fine lines here. And that is because the temperature is lower, and so we'll find that the energy for the elements required to absorb and re-emit light is of the right level for it to occur. So you'll see that certain elements are visible here, which aren't visible at all up here. If we go cooler still, then calcium becomes significantly stronger. So one of the hallmarks of a K-class star is that the calcium lines are at their strongest. And then we get to M-class stars. Here the temperature is so low that even molecules can exist and absorb and re-emit. And so you'll notice here that not only do we have lines of elements, but then we also have lines of titanium oxide, for example. So in that case, these cool stars, you can see, have lots of absorption lines, and that's only found in the relatively cooler stars. So analyzing the spectral lines allows us to determine the temperature simply by looking at the strengths of the various lines.
So now you can see that we can find the composition of a star by looking at its banding pattern. Remember again that this is the absorption spectrum, so that these black lines these 4 black lines show where hydrogen absorbs that particular wavelength of light. So after viewing that video where the professor is doing the demonstration of actually looking at the nitrogen, etc., you should be able to say that when you're looking through a spectroscope at the banding patterns of light sources, that there is a difference between the light spectra produced by different types of lights. What is that difference? Well, different types of elements are going to have different banding patterns. That's very obvious. And then the question as well then is, how did the spectra from the gas discharge tubes, so those were the individual neon, mercury, hydrogen, etc., how did that differ from the spectrum that you saw produced by the light source? The light source was the incandescent bulb at the beginning of that particular shot. So when we looked at the gas discharge tubes, we were actually looking at some light bands coming through with lots of darkness. That's because this was from an emission spectrum. What we did was excite the gas within the tube, and then as those electrons were letting go of the energy that we gave them from the electricity, they were throwing off very, very distinct patterns of light. So you can see the light bands showing up when you have the gas discharge tubes. But when you looked at the full light source, what you actually saw then was lots of color with maybe a few dark bands. Let's say we were looking at the fluorescent light. There were a few dark bands in there. If you were looking straight at the sun as your light source, we can see that it is a full wash of color because the sun is going to supply all types of light to us. So we'll see a full spectrum. Okay, less bands in the tubes, less elements in the tubes. Compared to the sun, when we look at that, it'll have a lot more banding patterns and whatnot because we're looking at more than one element. Now here's a good test question. How could knowledge of the banding patterns for different elements help astronomers to determine the composition of stars? Well, quite simple, what we've already discussed. You look for the distinct banding patterns made by each unique element. So can you see lines there for hydrogen? Can you see lines for helium? Well, those are the bands that are present in the star spectra. So what does all that star spectra stuff have to do with Edwin Hubble? In his second proposition, he said that almost all galaxies were moving away from each other. How did he know that? Well, what Hubble did is he looked at something called the Doppler shift. Let's just explain Doppler shifts in a very basic way here. Light energy travels a lot like a wave, kind of like the wave of an ocean, and moves a lot like sound would. Right? When an object is stationary, which means that it stays in one spot, so for example, a duck sitting on the water, if it was just staying in the one spot, you would see these little waves moving out from it evenly in all directions away from the duck. Okay? And you would see that the distance here and the distance between the next wave and the distance between the next wave, that is all the same. Distance between waves is called wavelength. You'll learn more about this in grade 10. So here you have the peak of a wave and another peak of a wave, that's the wavelength. You can also measure the wavelength from the very bottom of a wave to the bottom of a wave, or from the middle of a wave to the next time it's on its way down, or from when it's on the way up to when it's on its way up. Doesn't matter. As long as you have a repeating point, that's the distance of a wave. Okay, it's the distance between two repeating points on a wave. So here we see that when something is stationary, all of those waves are exactly the same distance apart. But when an object is moving, so now this duck is moving, you can see that the waves in front compress or shorten, and the waves behind get longer and longer and longer compared to the original movement of the duck, where it was staying stationary. So we have in front, we have compression or shortening of the waves, and behind we will stretch or lengthen those waves. Now, if you were listening to sound and you heard short waves, you would have a high pitch, very high pitch sound. If you were listening to long waves of sound, it would be a very low pitch sound. Think about the last time you heard an emergency vehicle. Were you able to tell whether that vehicle was coming towards you or away from you? Listen to this sound and see if you can tell whether the ambulance is coming towards you or away from you. Or better yet, are you able to tell the point when it's coming towards and suddenly changes to going away from you? So what's going on here? Why are you getting a sudden change from a very high pitch to a low pitch as the vehicle passes you? Well, watch this little animation and it'll give you an idea of what's going on with the wavelengths.
So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up and so are delivered to you at a higher frequency, which you interpret as a higher pitch because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out and so you hear them at a lower frequency, a lower pitch.
Now, when you're dealing with light, short waves are the blue end of the light spectrum, and long waves are the red light side of the spectrum. Please remember this. Memorize these light ones here because it'll matter when you're trying to figure out exactly what's happening. So remember that. If they are much, much shorter, then they would be high pitch in sound and blue light rather than just the normal colored light. And then if they are wide and behind, that would be a very low pitch sound, and it would be a red light that you would see. Now here's where you are standing in relation to the duck. Let's put you now in relation to a star.
So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth.
If this is you, and this is the star that you're looking at, if neither of you are moving, you should see the distinct banding patterns that tell you what elements are in that particular star. Nice and easy. However, if the normal banding elements seem to be shifted towards the blue, then that tells you that the wavelengths have all shortened. If they've shortened, it means that that star must be coming towards you. So we would say that when a star is approaching you, you see a blue shift in the spectral lines for each of those elements. If the star is moving away from you, that should spread out the waves that you're looking at, and so you would have longer wavelengths on your side of the star, and you would see it shift. Here's the original line, and you would see it shift towards the red direction. So we would say then that a blue shift is when something is moving towards you, and a red shift is when something is moving away from you. Keep in mind, maybe you're the one that's moving. It is possible. A star could be stationary, and then as you come towards them, you could see a blue shift or you could see a red shift if you were moving away from that star. But in general, we're talking about the motion of the stars. So this answers the question of how did Hubble know that the stars were actually mostly moving away from us, some towards and showing the blue shift, but lots, many, many more are showing this red shift pattern where the spectral element patterns are shifting towards the red.
Now the next thing I want to look at is translational motion. What do I mean by that? Well, is the star moving towards you or away from you? And can we tell whether a star is moving towards you or away from you simply by analysing its spectra? And we can. The first thing is to say, well, what does a star look like if it's stationary? And so you will get a normal spectra. So you'll have a wavelength of light, and I'm just going to be representative, that looks something like this. So you're going to have sort of the wave coming a little bit like this with its characteristic wavelengths or range of wavelengths. I'm just using this as a diagram here. But what happens if the star is moving towards you? Well, if the star's moving towards you, what we're going to find is that the wavelengths get a little bit smaller. So in other words, it sort of pushes closer together, like so. And we call this a Doppler shift. Now, it isn't a Doppler shift where the speed of the wave changes, but the frequency does increase, or the wavelength decreases. And what that does to our spectra is that it shifts it towards the blue. You'll see that each of these lines line up sort of as in with relative to each other, but there is a shift towards the blue. That is, each of the lines have moved just a little bit in that direction. And so we say it's blue shifted. The amount of blue shift determines, for example, how fast the star is moving towards you. Now, what if the case the star is moving away from you? I guess you can work out what's going to go on. Then what we're going to get, and again I exaggerate this here, is we're going to get a wavelength that is longer. Again, I'm really exaggerating this here. The wavelength gets longer, the frequency gets lower, and if the star's moving away, as a result, you're going to find that in this case, the light causes the spectra to shift towards the red end. So we say it's red shifted in that direction. You can see every single one of them is shifted towards the red. And again, the amount of shifting will allow you to calculate the relative motion. Now, of course, it could be our motion as well. So in other words, if we are moving towards the star, that is, of course, going to cause a shifting as well. Final one I will look at is rotational motion. And that is, a star, of course, isn't stationary. It's also going to be rotating. Now, if it's going to be rotating, what does that do to the spectra? The first thing is that the light at the center moving in that direction is just going to give us a normal wavelength of light, like so. However, this far end here is moving away from you, so that's going to give us a little bit of a red shift. So in other words, the wavelength is going to be a little bit longer. However, the lower margin is moving towards you, which means we're going to get a much shorter wavelength. Well, not much shorter wavelength, but definitely shorter. But you're going to get all three at the same time. So this line is going to not move one way or the other, but it's going to move both. And that means the lines become slightly broader. Now, this is not fuzzier, this is simply broader or fatter lines. And that's again indicative of the rotational motion of the star. And of course, both can happen at the same time. So if you find that the lines are broader, but also shifting, let's say, towards the red, then the star is not only rotating, but it is also moving away from you as well.
Please take a look at this activity and make sure that you run through and see if you can tell which elements are in each of these stars based on the information I've already given you. And that concludes this lesson.